This tutorial is about automated analysis of histological sections of muscle fibers in the Baxter algorithms. I assume that you've already watched the tutorials about running the program and specifying settings for fluorescence channels. So here I have two image sequences where GFP positive cells have been transplanted into muscle of two different animals. The first thing we need to do to process these image sequences is to get some settings for segmentation. We can do that either by going directly to the set segmentation parameters, or we can load settings using the load settings menu option. And in this case we would load the high background settings for fiber segmentation, because these images were created using wide field fluorescence microscopy, and there the background is pretty high compared to confocal microscopy. But we'll go to the segmentation settings user interface directly, because here I can show you all of the settings that need to be specified in order to segment these images correctly. So the segmentation algorithm needs to be segment fibers. It's a special algorithm designed for segmentation of this type of fiber images. And the segmentation channel has to be laminin. The laminin channel is the extracellular matrix channel, which is red here. So the fiber boundaries. And here we see that we have a lot of under segmentation, and to cope with that we should use this setting, set merge threshold, and this says that the intensity of a boundary between two fibers has to be 3 times as high as the intensity inside the fibers, and here the difference is much less than that, so we'll decrease this to 2. That gave better results. I think we can get even better results if we decrease it further to maybe 1.5. We still have some under segmentation here, for example, and here. Hopefully this under segmentation will be removed now. This looks pretty good. There's another setting here where we can specify a background threshold. So everything below this threshold will be considered background, and that can be useful to remove cracks between tissue regions. But here the intensity inside the cracks is roughly the same as the intensity inside some of the dim fibers. I don't think it will work, but we can set it to 0.05. So now we removed way too much. So maybe it should be 0.03. As I said, I don't expect this to work properly. You can see that the fibers with high intensity are still here, but the dim fibers have been eroded. So here we see that we've removed some regions in the cracks, but we've also removed some regions inside fibers. So the best thing to do here is to just set the threshold to 0, and then if necessary we can manually remove the cracks in the manual correction step. If we're only interested in GFP positive fibers, we won't even have to remove them manually. We can just analyze the data, and these cracks will be considered GFP negative fibers. So I think these settings are good for this image sequence. I'll save them for this sequence, and I unpress the revert to saved button, and we'll look at the second image. Now that I don't have revert to saved pressed, the settings from the previous image sequence will be applied to this, or the settings for the previous image will be applied to this image as well. And this looks very good. So I'll save it for this sequence as well. And then we go to automated track. The program sees this as tracking of an image sequence with a single image in it. And I'll use 2 processor cores because then I can segment them in parallel. And I'll enter a note here. Now that the processing is finished, we go to manual fiber correction. The fiber correction user interface is similar to the track correction user interface, but it's been designed specifically for correction of fibers. Here we can look at the segmentation result. We can, for example, turn the dots in the middle off the tracks, and we can also color all of the fibers in a color. If we color them all white, maybe they will be easier to see. I'm not sure that this was easier to see, so I'll go back to the original coloring. Here I can perform corrections. I can delete or undelete objects. For example, here this is a crack between tissue regions. At least I think so. Sometimes be hard to tell even by eye. If we turn both dots and outlines off, we're going to be able to see more clearly what's a crack and what's not a crack. So maybe if we have only the dots, we can remove the dots and the cracks. I don't think this is going to be necessary because we're only interested in the GFP positive fibers in this case. But if you're interested in both positive and negative fibers, you're going to have to do this. I think I've removed all of the cracks now. Oh, there's one more. I can also set positive and negative fibers if I want to. And for that there's a special coloring. So now all of the fibers are considered negative because they're green. Positive fibers are red. So if I press this, or I press this tool here, then I can specify which fibers are positive. Oh, now I accidentally turned the display of positive fibers off. But here I can see the positive fibers that I just entered. Now here's a fiber which should actually be 2 fibers, and then I can use the segmentation editing tool to separate these two, and then I get 2 fibers, and this object should actually be a true cell and not a false positive. For these two, I'm gonna have to look at I think this is actually 2 fibers as well. You might not have to do all this. It depends on how sensitive your analysis is to errors like this. But most of the fibers are segmented correctly. And I'm not gonna do this manually. I'm going to let the program decide which fibers are positive and which are negative. So I will just make all of these fibers negative again. And then I'll save the results. And I just entered corrected at the end. Save it. Then I go to the next sequence. And I use the same coloring as before. I think this looks good, but we have some fibrotic tissue here which is not fibers, and therefore I'll just remove these. This is also not going to be necessary for the analysis I'm going to do, but I'll show you just so that you know how to do it. It's sometimes hard to see what is a fiber and what's not a fiber. But I think this looks good to me. Save the results. And then I go to the analysis user interface for fibers, which is here. I select which image sequences I want to include. I also need to specify the imaging conditions, or not the imaging conditions, but the and I also need to specify the and I also need to specify the experimental conditions for the 2 images. I go to settings, analysis, and then this one I'll call G2 G2, because it's just the mouse, the recipient mouse and the donor mouse, and we WT G2. Now I have two different conditions here. Press save, and then I can perform the analysis. Here is I select the results that I want to process. I want to bring the images by conditions. I want to analyze the fluorescence in the GFP channel. This specifies that I want to analyze the intensity across the entire fiber. I can set this to 5 pixels, for example, and then only the outermost 5 pixels on each fiber, just a fiber border, will be included in the analysis. That's interesting if you want to analyze a surface receptor or something like that. I'll use the median intensity as my readout, because the mean intensity can be affected by grains of secondary antibody. And I'm going to threshold the fluorescence automatically. I'll use separate thresholds for the two images, because they may have different brightness. I'm not going to normalize the intensity by the threshold. And here I'll just perform all of the analysis that you can perform. And when I press start, the analysis starts. First I need to say where I want to save the Excel file that's created with analysis results. And I will save it on the desktop. And now the processing is finished. Plot shows the GFP expression as this plot shows the GFP expression plotted against the fiber area in pixels. Here we can't really see a trend, just from two images. Here we can see the fiber area in pixels, just a distribution, and we see that in the wild type mouse, the fiber area seems to be a little bit larger. But you need a lot more images to make any conclusions. This is just a trial. Here we have the fiber intensity, or the fiber intensity in the fibers. Here we have the fluorescence intensity inside the fibers. And this plot is weighted by the fiber area. So a big fiber will contribute more to this than a small fiber. And that can be reasonable, because then you're looking at the tissue and not the individual fibers, and the results won't be skewed by a small piece of tissue with very small fibers, because then small fibers will increase the. This plot shows the fluorescence intensity inside the fibers, and in this case the density is weighted by the fiber area. So large fibers affect the density more than the small fibers, and this can be good because then a small tissue section with lots of fibers won't skew because then a small piece of tissue with a huge number of small fibers won't skew the results. This plot shows the fluorescence intensity inside the fibers, and the intensity has been This plot shows the fluorescence intensity inside the fibers, and to generate these distributions, the fiber intensities were weighted by the areas of the fibers. And this can be good because then a large fiber will affect the density more, and then a large number of really, really small fibers won't skew the results. Let's see here. Here's an interesting plot where we show a heat map of the intensity in fibers that were considered positive for GFP. So the thresholding is computed automatically using a fit of two Gaussian distributions, one for the background and one for the foreground, the GFP positive fibers. This looks reasonable, and so does this plot of the positive fibers. Here is the same thing, but here we show the intensities of GFP negative fibers as well. And here is an overlay on top of the original image where we show the GFP positive fibers outlined in gray. If we open the Excel sheet with the results, we have the fiber sizes in the If we look at the Excel sheet, first have the areas of the fibers, and we have some statistics for the two experimental conditions. So if we look at the Excel sheet, we first have the fiber sizes or the fiber areas in pixels, and we've got some results for the two experimental conditions. In this case, we have a single image in each condition, and therefore the combined results are the same as the results for the images. But in the first condition, where we've transplanted cells from a If we look in the Excel sheet, we first have the fiber sizes in pixels, and then we have statistics for the two experimental conditions. In the first condition, we've transplanted cells from a transgenic mouse into a transgenic mouse, and in the second, we've transplanted wild-type cells into a transgenic mouse. If we look at the Excel sheet, first have the fiber sizes in pixels, and then we've got some statistics for the two experimental conditions. In this case, we have a single image in each condition, and therefore the combined results are the same as the results for the individual images. In the first condition, where we transplanted transgenic cells or cells from a transgenic mouse into a transgenic mouse, if we look at the Excel sheet, we first have the fiber sizes in pixels, and then we've got some statistics for the two experimental conditions. First experimental conditions, we transplanted cells from a transgenic mouse into another transgenic mouse. The second condition, we transplanted wild-type cells into a transgenic mouse. And given that we have only one image per image, if we look at the Excel sheet, we first have the fiber sizes in pixels, and then we have some statistics for the two experimental conditions. So given that we have a single image in each condition, the combined results are the same as those for the images. In the first condition, where we transplanted cells from a transgenic mouse into another transgenic mouse, we had 152 positive cells. And in the second experimental condition, where we transplanted wild-type cells into a transgenic mouse, we had 374 positive cells. This is representative of the experiment, but we can of course not say anything for sure just by looking at a single image like this. This is just an example. And here we also have some statistics over the intensity of the GFP in the fibers, the fiber areas, the GFP in the tissue, where we haven't computed it for each fiber, it's just a pixel intensity inside the tissue consisting of positive fibers. And here we have a measure of the total amount of GFP in the positive fibers. And we also have some explanations for these parameters here at the bottom of the Excel sheet.